This might sound absurd at first. In a universe packed with stars in every direction, darkness shouldn't exist at all. Yet every night, the sky is dark. That contradiction is not a mistake, it's a clue. So what is the darkness really telling us about the universe we live in? We are used to treating night as a backdrop, a neutral pause between days. Something ordinary. But when you slow down and think carefully, that familiarity begins to fracture. Light travels. It does not hesitate. If stars truly filled space endlessly, their glow should stack upon itself, layer after layer, until the sky burned white. There should be no shadows left for night to occupy. And yet, here it is. Above us stretches an ocean of black, broken only by scattered points of light. Not overwhelming, not continuous, sparse, measured, almost deliberate. The absence is impossible to ignore once you notice it. Darkness is not merely what remains when lights turn off. It is structured. It has boundaries. It arrives with rules. The answer to this paradox is not hidden in the behavior of stars alone. It reaches deeper into how space is arranged, how time moves, and how far information can actually travel. It forces us to confront a quiet limit. There are regions of reality we cannot yet see, not because they are empty, but because the universe has not had enough time to show them to us. By following this single contradiction, we begin to uncover how humans learn to measure distances that dwarf intuition, why space is neither static nor eternal, and how the familiar darkness overhead carries the imprint of a universe that is unfinished, still unfolding, and constrained in ways our instincts never prepared us for. The more we learn about that unfinished, unfolding universe, the more one quiet truth sharpens in the background. Whatever this whole structure is, we are seeing it from the smallest possible balcony. Imagine holding a single grain of sand between your fingers at arm's length. Rough edges, almost weightless, easy to lose. In many ways, our sun is like that grain, not in size, of course, but in importance. One ordinary star, in one ordinary arm, of one galaxy. It feels like home only because we have never stood anywhere else. Astronomers estimate that our Milky Way contains on the order of a few 100 billion stars. That phrase sounds heavy, but the mind slips on it. Hundreds, billions. Our language tries to stack meaning, but it never quite lands. If, instead, you tried to count those stars one by one, naming each as if it mattered, even whispering one every second without sleep, you would still be speaking long after your lifetime ended, and the total would barely have moved. The galaxy would go on shining, unbothered by the fact that you ran out of time. Already, there is a quiet dislocation here. We are used to thinking of ourselves as the main characters of the story, but from this vantage point, we are not even a full sentence. We are a comma, an intake of breath, a pause between larger events. Now stretch the image further. That first grain of sand is our sun. Around it, an almost empty volume we call the solar system. The nearest star beyond our sun is so far away that if the solar system were shrunk to the size of a coin in your palm, the next coin would be another room away. Between them, nothing you could see or touch. Just distance. Just separation. Light, moving faster than anything else allowed by physics, takes a little more than 4 years to bridge that gap from our sun to that next star. Not 4 years of human habit, marked by birthdays and seasons, but 4 continuous years of motion at the maximum possible speed, without ever stopping to rest. And that is just the first step outward. One neighbor, one small hop in a galaxy whose disk is so wide that light needs on the order of 100,000 years to cross from one side to the other. 100,000 years of relentless travel, just to go from one edge of our city of stars to the other side. At this scale, a human life compresses into a brief flicker. A person could be born, live fully, love, suffer, wonder, and die. And in all that time, a ray of light would not even have made it all the way across the thin neighborhood around our own star. Our entire history, written in wars and symphonies and quiet conversations in dim rooms, fits into a sliver of time so narrow that the galaxy itself would not notice. And yet, from this barely significant vantage point, people have tried to reconstruct the whole. When early civilizations looked up, they saw patterns. Hunters, lions, scorpions, woven from stars that only seem close because they share the same two-dimensional sky. The constellations are evidence of a human impulse to project stories onto distance, to tame the scale with familiar shapes. It is not wrong, just incomplete. The same stars that form the outline of a mythical figure might be separated by hundreds of light years in depth. They do not know they belong to our picture. They simply burn. Still, those pictures served a purpose. They gave people a way to navigate seas, to mark seasons, to anchor ritual. They turned the sky into a ceiling just high enough to feel safe under. The vastness beyond remained implied, but unspoken. As telescopes grew more powerful, that ceiling cracked open. What had looked like smooth, constant light resolved into innumerable points. The hazy glow of the Milky Way, stretching like spilled fog across the sky, broke apart into a river of stars. Each one a sun in its own right, each one possibly surrounded by its own set of worlds. Here the scale begins to feel almost adversarial. The observable universe, the region from which light has had time to reach us since the beginning of cosmic expansion, contains an estimated few 100 billion galaxies, each with its own population of stars. This is not poetry. It is a measured consequence of how far light can travel in the age of the universe, combined with how galaxies cluster and evolve. When you try to imagine it, your thoughts do not simply stretch, they snap. And yet, obscenely, we are trying to talk about all of this from the surface of a single small planet, orbiting that one grain of sand. There is a kind of quiet courage in that, to accept that we are not central, not large, not timeless, and still attempt to map the whole. From a purely physical perspective, we are fragile arrangements of atoms on a rock, clinging to a thin layer of air. From another perspective, we are the part of the universe that has become able to look back at itself and ask why there is darkness between the stars. This contrast is difficult to hold. On one hand, we are cosmically insignificant. On the other, our ability to understand even a fraction of the cosmos is outrageously rare, at least as far as we know. The same mind that worries about unfinished messages and unwashed dishes can also calculate the age of the universe. From the faint glow of distant background radiation, the ordinary and the incomprehensible share the same brain. Consider distance again. The light from our sun takes about 8 minutes to reach Earth. That does not sound like much, until you realize that when you look at the sun never directly, always with protection, you are seeing it as it was 8 minutes ago. The sun you react to is already in the past. Extend that idea outward. The starlight scattered through the night sky is an archive of different times. Some of those stars may have ceased to exist by now. Their lives ended in violent explosions. Yet their light is still mid-journey, still crossing the space between, still arriving in our eyes tonight as if nothing had changed. In this way, the sky is not a picture of the universe as it is, but as it was, smeared across time. We never see the present. We see layered histories, each arriving late by a different amount. Our vantage point is not only small in space, but deeply provincial in time. This has an unsettling implication. We move through our days assuming that what we see is what exists. A chair, a tree, a person walking past. Here, now. But on cosmic scales, now is not a single shared moment. It is a local condition. The universe does not grant us a universal present tense. It offers us instead a patchwork of delayed signals, and we stitch them into a story that feels continuous. Standing under the night sky, you are surrounded by evidence of this delay. That gentle star near the horizon might be 100 years out of date. Another, higher and colder in color, could be 1,000 years behind. A faint smudge that looks like a tiny cloud may in fact be a galaxy whose light has been traveling toward you for more than 2 million years. While that light was in transit, entire civilizations rose and fell on Earth. Languages were born and forgotten. Entire eras of human history unfolded. And through it all, those photons simply continued, indifferent, until they finally ended their journey in the back of your eye. The more honestly we face this, the more one realization sinks in. Our sense of being at the center of things is a local illusion. It is not that we are nothing. It is that we are small participants in a far larger process, one that began long before us and will continue long after. Whatever meaning we build has to be constructed within that small window, aware of its limits, not pretending they do not exist. And yet that limit is strangely empowering, because it is precisely this narrow vantage point that forces us to develop methods that reach beyond what our senses can handle. We build telescopes that collect light too faint for our eyes. We launch observatories into space to escape the blur of the atmosphere. We measure tiny shifts in wavelength to infer motion and distance. We compare the brightness of certain kinds of stars, not by eye, but through careful calibration and mathematics. Step by step, we extend our reach without ever leaving home. In doing so, we admit something important. The universe is not arranged for our convenience. If we want to understand it, we must work with what little reaches us. That sliver of information, carried on fragile beams of light, is all we have. But it is enough to reveal that the darkness overhead is not emptiness. It is limitation. It is the visible edge of what light, and therefore knowledge, has had time to deliver. This is where the shock of scale becomes more than an abstract idea. It is not just that the universe is large. It is that our lives, our questions, our fears, all unfold inside a very small, very temporary observational bubble. The night sky is not a vast open window. It is a small round porthole in the side of something much larger. Most of the ship is still hidden from us, and yet we press our faces to the glass. We measure, we infer, we argue, we revise. From this smallest vantage point, we have already discovered that the universe has a finite age, that it is expanding, that its large-scale structure is shaped by matter we cannot see directly. None of this was obvious. All of it arose from the stubborn decision to take our smallness seriously, rather than pretending it can be ignored. The paradox of the dark night sky rests on this shock of scale. If the universe were truly infinite, unchanging, and filled evenly with stars, then our smallness would not matter. Every direction would be overwhelmed with light. There would be no room left for ignorance, no shadows for questions to hide in. The fact that we do see darkness, that we can look up and find more absence than presence, is the first hint that the universe is not the simple, boundless stage it once appeared to be. To follow that hint, we have to keep accepting what the shock of scale keeps telling us. We are small. Our window is narrow, and yet within that narrow frame, the universe has already told us more than we were ever supposed to hear. Once you accept that the window is small, another question quietly appears at its edge. If we keep pushing our gaze outward, past everything we can name, past everything we can measure. Then what comes after that? For most of history, this question did not start with equations. It started with a body lying on the ground. Imagine someone on a cold, clear night, long before telescopes, long before maps of galaxies. No city lights, no engines, just breathing, the faint rustle of wind, and an unfamiliar feeling of having nothing above them but sky. At first, the stars seem close, almost domestic. They fit neatly into patterns that match the stories of the day. Hunters, animals, gods. The sky behaves like a painted ceiling, curved gently overhead. Then, slowly, a different thought forms. If you could rise up through that ceiling, if you could keep going, what would you meet? The mind does what it always does. It starts layering imagined shells. First, the air, growing thinner. Then the region of storms and clouds. Above that, a place for the moon, for the wandering planets, for the sun. Beyond them, a final surface where the fixed stars are attached, like bright nails in a dark dome. A last wall, a limit that reassures, for a very long time. That final wall felt natural. It matched what the eye reported. The stars did not rearrange themselves night to night, except in tiny, slow changes that were easy to miss. The patterns returned with the seasons. The dome turned, but the dome itself seemed intact. If you had asked that person on the ground, "And then what?" they could have given you an answer. After the stars, there is an outer boundary. Beyond that boundary, perhaps a realm of the divine, or nothing at all. But at least the picture closed. The question had a lid. Under that view, Earth sat near the center, wrapped in concentric layers. The cosmos was structured like an onion, each shell carrying its own kind of object and motion. The human world, at the core, felt grounded. The heavens, above, were flawless, unchanging, perfect. The sky was not a mystery to wander through. It was a finished ceiling built with intent. What is striking is not that people believed this. It is how reasonable it feels when you put yourself back in that position. Without instruments, without a sense of the true scale. The idea of an enclosed universe is not childish. It is almost inevitable. The brain takes the limited data it has and completes the picture in the simplest possible way. In that completed picture, the first question, "And then what?" has a comforting answer. After the last shell, you are done. There is nowhere else to go. Curiosity can rest. But even in those early centuries, small doubts were already hiding in plain sight. Stand at the edge of the sea and watch a ship leave the harbor. It does not simply become smaller and smaller forever. At some point, the hull disappears. Then the sails, as if the earth itself is swallowing the vessel from below. That vanishing act suggests something curved, something larger than the flat surface it appears to be. If you walk long enough in one direction, following the sun, you will eventually circle back close to where you started. The routes of explorers and traders, traced on later maps, reveal that our planet is not endless land bordered by a single ocean. It is a sphere, with a size that can be measured. The distance around Earth at the equator, its circumference, is a little over 40,000 kilometers. That measurement does more than describe our world. It quietly does something to the sky as well. Because if Earth is a sphere, hanging in space, then those shells above are no longer resting on a solid foundation. The ceiling begins to float. Once Earth becomes a globe, spinning beneath the stars, other rhythms fall into place. Day and night follow that rotation. Our planet turns once relative to the sun in what we call a day, and once relative to the distant stars in a period slightly shorter than that, a sidereal day. The time it takes Earth to complete a full rotation with respect to the fixed stars. is a little under 24 hours. For someone lying on the ground, the details of that timing are invisible. What they do feel, though, is the regularity. Sunrise, sunset, the familiar swing of shadows. It is easy to believe that this rhythm belongs to us, that it is tuned to human life. In reality, our lives have been braided around an impersonal cycle set by a spinning rock, long before anyone named it. The moon adds another layer. Night after night, its shape shifts. A thin curve thickens into a half circle, then a pale disk, then retreats again. Those phases are not moods. They are geometry. The moon moves in orbit around Earth, so that different portions of its sunlit half become visible to us over time. The time it takes the moon to complete one orbit relative to the distant stars is a little more than 27 days. Again, before there were measurements, there was only the pattern. People knew that certain tides, certain planting times, certain rituals clustered around particular phases. The moon's cycle became a calendar written in light and darkness. It nested neatly within the larger cycle of the year, which followed the path of the sun. The sky, taken as a whole, looked like a set of concentric clocks, all turning with reassuring regularity. Against this backdrop, the first question feels almost innocent. If there is Earth, and then sky, and then stars, and then a final shell, what lies beyond that last layer? Is there an outer surface of everything? And if there is, what is on the other side? For those early thinkers, there were several ways to answer. One was to place the divine beyond the final sphere, in a realm untouched by change. Another was to imagine a surrounding void, empty and irrelevant, because nothing in it could ever touch us. Either way, the structure remained closed. The important part, the part where stories and lives unfolded, was safely inside. But the question has a way of not staying quiet. Once you allow the possibility that Earth is not central, that it moves, that it turns, a new unease enters. If our world is just one object among others, if the sky is not a ceiling but an environment, then perhaps the last sphere is not final either. Perhaps, and then what, does not stop at the stars. Think of the distance to the moon. On most nights it hangs there, looking close enough to pinch between thumb and finger. In reality, it is, on average, about 384,000 kilometers away from Earth. That gap is vast enough that you could line up the entire Earth in that space many times. Yet even this scale, once understood, becomes another stepping stone. If the moon can be that far and still feel near, what does far even mean beyond that? As these insights accumulated, the neat, layered cosmos began to loosen. The spheres that once carried planets became less like crystalline shells and more like orbits traced in empty space. The stars, once pinned to a single surface, began to drift in thought, each perhaps in its own position, scattered through a volume rather than glued to a dome. The universe started to look less like a closed room and more like an open field. The first question, and then what, changed character with this shift. It was no longer about what lay beyond a rigid outer wall. It became a question about extension. If space is not a surface but a volume, if there is room for objects to be at different distances, then how far does that room go? Does it end somewhere? Or does it keep going without limit, lying under the stars? The question can feel almost physical. You imagine yourself rising, higher and higher, passing the altitude where planes now fly, passing above the path of satellites, drifting beyond the orbit of the moon, beyond even the reach of the sun's light. As it grows thinner, the familiar grows small, then vanishes. You keep going in your mind, because nothing stops you. No wall appears, no sign saying, "End of universe." Your imagination never hits an edge. At some point in that mental ascent, a strange tension appears. On the one hand, an endless universe feels natural. Why should there be a boundary? What would it even be made of? On the other hand, actual infinities are hard to live with. If space truly extends forever, if stars continue without end, then that simple night sky above you becomes something very different from what it appears to be. This is where the first question becomes dangerous. In a quiet way, it begins as a naive curiosity. What comes after? Pushed far enough, it threatens the entire picture of a safe, contained cosmos. If there is no final shell, if space goes on and on, then the stars cannot all be nailed to one surface at the same distance. They must live at different depths, stacked along your line of sight. And if that is true, if every direction hides more and more stars at greater and greater distances, then the dark gaps between them start to look suspicious. Because in such a universe, should there be any gaps at all? The people who first lay under the sky and asked, "And then what?" did not know they were setting off a chain of thought that would eventually make the darkness itself problematic. They only knew that the question would not leave. Once raised, it lingers. It follows sailors to sea, priests to observatories, philosophers to their desks. It waits behind every new instrument pointed upward. Each new measurement of the size of Earth, of the length of its spin, of the distance to the moon, of the rhythm of the heavens, chips away at the old enclosed model and pushes that first question a little further out. At some point, quietly, the lid comes off. The universe is no longer a room with a ceiling, and once the ceiling is gone, the darkness above stops being a simple backdrop. It becomes a puzzle. That puzzle did not arrive all at once. For many people, it began with a single night when the sky broke its own rules. In the late 16th century, people still trusted the heavens to behave. Earth could be chaotic, plagues, wars, failed harvests. But the sky, with its slow, regular turning, seemed to belong to a different order. Above the messy world of change stretched a realm of perfection, sharp and distant and complete. Stars did not appear or vanish. They simply were. Then, on the 11th night of November, in the year 1572, something new flared into existence in the constellation Cassiopeia. Observers saw, where there had been only familiar faint stars before, a piercing point of light as bright as the brightest planet. It rivaled Venus, and for a time it could be seen even in the daytime, a hard, unblinking presence in the blue. For those who lived through that night, the experience was not abstract. It was not a tidy diagram in a book. It was a shock to the senses. Imagine looking up at a pattern you have known your whole life, a pattern you have been told is eternal, and finding a new star burning where no star should be, not drifting slowly into view over centuries, not revealed by a new instrument. Just there, all at once, as if someone had driven a fresh nail through the firmament. People reached for the frameworks they had. In some places, the appearance of the new star was read as a sign, a warning, a celestial comment on the affairs of kings and kingdoms. In others, it was folded into religious narratives, an omen of judgment or change. When the sky, the supposed realm of perfection, starts doing unexpected things, it is hard not to feel that the story of the world itself has been altered. Among those who saw it was a Danish observer, Tycho Brahe. He was not the only one to notice the new light, but he was one of the few who approached it with a stubborn, methodical patience. Night after night, he measured its position against the known stars. Using instruments built with unusual care, he was looking not for drama, but for geometry. According to the traditional model, anything that appeared and disappeared belonged to the realm beneath the moon, the region of corruption and change. The crystalline spheres of the fixed stars, far beyond, were supposed to be unalterable, So, if this new object was part of the higher heavens, something was deeply wrong with that picture. The test was simple in principle. If the new star were close, somewhere between Earth and the Moon, its apparent position against the background stars should shift as Earth turned and moved. If it were truly distant, out with the fixed stars, that shift its parallax would be too small to see with the instruments of the time. Night after night, Tycho watched. Night after night. The new star refused to move in the way a nearby object should. In his great work, published in the year 1573, he presented a careful argument. Within the limits of his instruments, the new star showed no measurable parallax. It was, as far as he could tell, at least as distant as the old, established stars. The implication was quiet, but devastating. If the new light really shared the realm of the supposed fixed stars, then that realm could change. It had a before and an after. It could produce something that had not been there, something that would eventually fade. The high, perfect ceiling was cracked. The object we now call Tycho's supernova was not a small event. It was the death of a star in a catastrophic explosion. Its outer layers hurled into space at thousands of kilometers per second, its light briefly outshining the entire host galaxy that contained it. Modern measurements place the remnant of that explosion at a distance of roughly 13,000 light-years from Earth, in the direction of Cassiopeia. At that distance, the expanding shell of debris now spans an apparent size on the sky of about 8 arc-minutes across. A tiny circle to the naked eye, but enormous in physical extent. Of course, none of this was known in the 1600s. What people did know was simpler and, in a way, sharper. Something they had trusted as unchanging had changed. A region they had been told was incorruptible had clearly produced something new, and that something was bright enough to rival the most familiar lights in the sky. The object remained visible for more than 1 year, slowly fading, as if the universe were taking its time to insist that this was not a fleeting trick of perception but a real event. There is a particular unease that comes when a background you did not even realize you relied on begins to move. It is one thing for the weather to change, for rulers to rise and fall. Those belong to the foreground. They are expected to shift. It is another to discover that the frame around everything, the stage on which all stories play out, has its own history. The new star of 1572 forced a small but crucial adjustment in the human story. If the heavens could host explosions, if distant stars could blaze into being and then dim over time, then the cosmos was not a finished, polished object. It was an active place. It had episodes. It had events. For some, that realization was disturbing. A perfect, finished universe offers a certain comfort. It suggests that our uncertainty is purely local, that ignorance lives only in our limited understanding, not in the structure of reality itself. Once you allow that the universe is changing on the largest scales, the ground beneath certainty shifts. You are no longer living under a flawless dome. You are inside a process. And yet, within that discomfort, something else becomes possible. If the sky can change, then it can also be studied. It is no longer an untouchable symbol. It becomes a phenomenon. Tycho's measurements, taken with instruments far less capable than a modern amateur telescope, were among the first to treat the heavens with this new attitude, not as a realm to be interpreted for meaning, but as a system to be mapped, quantified, questioned. Centuries later, when we point X-ray observatories and radio telescopes at the remnant of that ancient explosion, we are still living in the afterglow of that shift. We see a tangled shell of hot gas and high-energy particles racing outward, the faint echo of a star that destroyed itself long before any human alive today was born. We map its expansion. We estimate its age. We compare its shape to our models of how stars die. But beneath all that calculation, the older shock remains. The sky, the thing that felt like the one constant in a life of changing details, turned out to have events of its own. It has a past we can uncover and a future we can only guess at, lying under a clear night now. It is easy to forget this. The stars look calm again. Cassiopeia has returned to its familiar shape, the new star, long gone to the naked eye. The heavens seem quiet, almost indifferent. Yet in that quietness is a memory. Once, not so long ago, on cosmic scales, a star tore itself apart there, and for a brief time the universe announced, to anyone who cared to look, that even its most distant ceilings are not finished surfaces, but changing fields of fire. The idea that the heavens are unfinished leads naturally to a harder thought. If the sky can change, who is to say it has an edge at all? In the generation after that bright new star, another kind of change unfolded. This time, not in the sky, but in the picture of the sky inside a single human mind. Thomas Digges, an English mathematician and astronomer, grew up in a world where the old Earth-centered model was already under quiet attack. Nicolaus Copernicus had proposed that Earth moves around the sun, not the other way around, and had published his great work in the year 1543. But books spread slowly, ideas slower still. Digges did not simply read Copernicus and accept a new diagram. He stepped into a conceptual gap that others had left untouched. If Earth circles the sun, if the planets are arranged in orbits around a central fire, what does that do to the outermost sphere of fixed stars? Does it still exist as a solid shell, or does it dissolve? In the year 1576, when he prepared a new edition of his father's work, Digges added a short treatise with a long title, A Perfect Description of the Celestial Orbes, according to ancient teachings, revived by Copernicus. In those added pages and diagrams, he did something quietly radical. He kept the sun at the center, as Copernicus had, with the planets circling it. But beyond the orbit of the outermost planet, he did not draw a hard boundary. He let the stars continue outward, not glued to a final surface, but scattered through an indefinite, perhaps endless, depth. For someone raised on nested crystalline spheres, this was not just a new layout. It was a different kind of universe. Instead of a closed container with Earth carefully placed near the middle, Digges pictured a cosmos that simply did not stop. The stars, those cold, distant lights, were no longer decorations on a dome. They became distant suns, extending without obvious limit into a surrounding infinity. It is difficult to reconstruct how unsettling this must have been. A finite universe, however large, can be imagined as a whole. You can, at least in principle, stand outside it in your mind and look at it as an object. An infinite universe resists that trick. There is nowhere to stand, even in imagination, where you can see it all. No outer surface, no last layer, just more. Digges' diagram shows the sun and the planetary orbits in the middle, surrounded by a field of tiny stars, each annotated with words about the innumerable regions and the palace of felicity extending outward. The drawing is simple, but the step it represents is not. He has taken the ceiling off the universe and refused to put another one back on. Here, the first hint of a deeper conflict appears. If the stars extend indefinitely, if there is no final shell, then all the comforting language of above and below begins to lose its grip. Earth is no longer at the center by design. It is merely one position among uncountably many. Whatever stories we tell about why we are here have to live with the possibility that there is no privileged vantage point, no preferred address in space. At the same time, this widening of the universe does something strange to the night sky. Once you allow stars at many different distances, stacked behind one another in every direction, it becomes harder to understand why the darkness between them is so deep. In a sense, Digg's infinite star field contains the seed of a later paradox, but in his time, the immediate shock was simply that space itself had opened. He was not working with the tools we have now. There were no precise star catalogues like those used today. No spectroscopes to read the fingerprints of elements in starlight. No clear way to measure how far away a star really was. The average distance from Earth to the Sun, which we now express as about 149.6 million kilometers, was still an uncertain quantity in his era, not yet pinned down to the standard we call 1 astronomical unit. Digg's was, in many ways, reasoning almost entirely from geometry, tradition, and imagination. And yet that imagination was disciplined. He was not simply making the universe larger for the sake of drama. He was following the logic of the heliocentric model to its uncomfortable conclusion. If Earth is a planet like the others, if the heavens have already shown they can host change, then what justification remains for a finite, enclosing shell of stars? Why not let them continue? There is a quietly human element here that is easy to miss. To draw an infinite universe is to accept that most of it will never notice you. In a closed cosmos, even if you are small, you still live in a finished structure. Your existence can be tied, at least symbolically, to the whole. In an open, unbounded universe, your life takes place in one tiny, local eddy of matter and light. The larger pattern, if there is one, does not bend itself around you. Yet rather than retreat from that implication, Diggs leaned into it. He translated, adapted, and popularized Copernican ideas in English, helping them step out of dense Latin texts and into a broader conversation. He was not only expanding space on the page, he was widening the mental room in which his readers lived. Imagine, again, someone lying under the stars. But now, after these ideas have begun to circulate, the constellations are the same. The bright points have not moved. But behind every pinprick of light is a new possibility, that it is one sun among uncountable others, spread through an enormous volume, with no reassuring shell at the edge. The simple question, and then what, now has an answer that does not close, only recedes. In that setting, the darkness between the stars acquires a different weight. It no longer belongs to a smooth, enclosing surface. It is distance, not paint. It is the unlit space between you and objects that might extend without bound. The blackness overhead stops being a sign of the universe's limit and becomes instead a measure of how far its contents might go. Modern cosmology has layered countless refinements onto this picture. We now talk about cosmic expansion, about horizons, about the finite age of the observable universe. We can compute how long Earth takes to complete one orbit around the Sun with great precision, a sidereal year of a little more than 365 days, and weave that into a detailed history of how the cosmos has evolved. But the emotional fault line that Diggs opened remains. On one side is the desire for a contained world, where the sky is a finished ceiling and our place within it can be neatly described. On the other is the acceptance of an open, perhaps infinite universe, in which our questions are not framed by a protective boundary, but by our own finite reach. Thomas Diggs did not resolve that tension. He simply drew it, gently, into the shape of the cosmos itself, and invited anyone willing to look up to live inside it. But once you dare to live inside that open universe, a new problem appears. It does not come from what you can see, but from what you cannot. Imagine the night sky again, not as a dome, not as a ceiling, but as a deep, three-dimensional field filled with stars at every distance. If space really stretches on without limit, and if stars are sprinkled through it more or less evenly, then a simple argument unfolds. Pick a direction, any direction. Draw a line outward from your eye into space. If the universe is infinite and filled everywhere with stars, That line should eventually hit one of them. If you slide the line a little to the left or right, it should hit another. If you look slightly above, slightly below. Same story, the further out you go, the more stars you cross. Now imagine not a single line, but a cone, like the field of view of your eye. That cone widens as it extends into space. The volume it covers grows. And if every part of space contains stars, then the number of stars inside that cone increases without bound as you extend it. Every distant shell of space adds its own population of suns. Even if each one looks faint on its own, together they add up. Light does something similar. It does not fade on its own. It spreads. The brightness of a single star falls off with distance because its light has to cover a larger and larger sphere. The same amount of energy is smeared over a wider surface, but if there are more and more stars as you go farther out, their contributions stack. In a universe that is both infinite in size and eternal in time, with stars scattered everywhere, the sky should not have dark patches between the stars. Every patch should be filled by the surface of some distant sun. This is the core of what later came to be called the night sky paradox. It is almost offensively straightforward. If space goes on forever, and if it has always been full of stars, then darkness should have nowhere to hide. The entire sky, in every direction, should shine with a brightness comparable to the surface of a typical star. The night should be as bright as day, though perhaps of a different color. You can try to wriggle out of this conclusion. Perhaps dust in space absorbs the light and keeps the sky dim. But dust is made of matter. Matter heats up when it absorbs energy. Over long enough times, that dust would warm until it glows as well, re-radiating the starlight it has swallowed. Given enough duration, the whole universe would drift toward a common temperature, an almost uniform glow, no deep blackness left. You might suggest that stars are not evenly spread out, that there are voids. True. The cosmos is clumpy. Galaxies gather in clusters and filaments, leaving great regions more empty. But on very large scales, as far as we can tell, the distribution smooths out. The cosmological principle, one of the basic assumptions of modern cosmology, states that on the largest scales, the universe is homogeneous and isotropic. It looks roughly the same in every direction and at every location. That principle, tested with observations of galaxies and of the faint background radiation that bathes space, seems to hold well. So the discomfort remains. A universe that is spatially infinite, filled everywhere with shining stars, and unchanging through endless time, leads directly to a prediction: no dark night sky. Yet each night, when clouds clear and city lights fade, you can look up and see that this prediction is emphatically not met. The stars are there, but they are sparse. Their light does not merge into a continuous sheet. Between them, blackness dominates. It is tempting to shrug and move on. The sky is dark because the sun is on the other side of Earth, because space is big, because stars are far away. These are not answers. They are reminders of the problem. The distance to the nearest large galaxy beyond the Milky Way, the Andromeda Galaxy, is about 2.5 million light-years. That means light has to travel for roughly 2.5 million years, moving through empty-seeming space before it reaches us. During that entire stretch, it does not slow down. In vacuum, it keeps its speed, about 300,000 kilometers every second. When you look at Andromeda with a small telescope, you are not seeing a weak, exhausted signal. You are seeing radiation that has completed a long, uninterrupted journey. If the universe has been around forever, and if it has always had stars like these, then every line of sight, extended long enough, should reach enough luminous surfaces to fill the sky. The fact that it does not is telling you that at least one of the assumptions in that sentence is wrong. There are a few possibilities. Perhaps the universe is not really infinite in size. It might loop back on itself in some complicated way, forming a large but finite volume. Perhaps it has not been shining forever. Stars may have had a starting point in time. Perhaps space, or the light moving through it, does something unexpected on very large scales, draining or diluting the radiation before it gets to us. The modern answer, the one supported by multiple independent observations, combines several of these ideas. It tells us that the universe has a finite age, that it is expanding, and that the light from very distant regions is stretched and cooled by that expansion until it no longer appears as visible starlight at all. The afterglow of the early universe, once blazing, now shows up as a faint microwave background with a temperature of about 2.7 Kelvin, a shade above absolute zero. In that thin hiss of radiation, measured by satellites orbiting Earth, the missing brightness of the night sky is accounted for. But in the historical moment we are sitting in now, in this story, that resolution is still in the future. For the thinkers who first took the infinite universe seriously, the paradox was less a solved puzzle and more an open wound. They had pushed past the comforting ceiling of the old models and stepped into an unbounded cosmos. Now that cosmos was talking back. Through the simplest of observations, it is dark at night. There is a deeper layer to this. The paradox is not only about light and geometry, it is about what it means to say that something exists everywhere. If you claim that stars fill space without limit, that the universe has always been populated by suns and galaxies, then the night sky becomes an experiment. You are not just making a philosophical statement, you are making a prediction that can be tested by anyone willing to look up. This is one of the quiet revolutions of this whole story. The ultimate structure of reality, which once seemed like a topic for pure speculation, becomes tied to an everyday experience. You do not need a telescope to notice that the sky between the stars is mostly black. You do not need complex mathematics to feel that this sits uneasily with the idea of infinite, eternal starlight. The universe, by allowing darkness to appear in such an ordinary way, has given you a lever to move its largest scale models. And there is something quietly unsettling in the role you occupy here. You stand on a small planet, circling an ordinary star whose surface is at a temperature of about 5,800 Kelvin. A star that has been burning for billions of years in a galaxy among hundreds of billions of others. You are brief. You are local. And yet you are in a position to notice a mismatch between the sky you see and the sky certain theories demand. In that sense, the paradox does something to the way we think about our place. It shifts us from being passive observers in a neutral backdrop to being participants in an argument the universe is having with itself. The darkness above you is not neutral. It sides against some possible universes and in favor of others. When you sit with this long enough, another question appears, more personal and harder to phrase. If even absence can be evidence, if the lack of light can carry information about beginnings and boundaries, then what else in your experience might work the same way? What other gaps, silences, or unfinished pieces are not just voids to be ignored, but clues to the shape of a larger story you cannot yet see? The night sky paradox stands at this crossroads. On one axis, it is a technical challenge. Reconcile the observed darkness with the idea of an infinite, eternal, star-filled universe. On the other, it is a reminder that something as simple as looking up can expose the limits of our assumptions. The universe, as described by theories, is one thing. The universe, as revealed by the fact that most of the sky is black, is another. Later, we will follow how that blackness led to the concepts of cosmic time, of expansion, of a universe with a history and perhaps a horizon. For now, it is enough to stay with the tension. You know that light in vacuum races along at a fixed, immense speed, the same everywhere, and that it has had a very long time to travel. You know that space, on large scales, is richly inhabited by galaxies. And yet, when night falls, what presses most strongly on your eyes is not light, but the vast, structured absence of it. The more seriously you take that darkness, the more you are pushed toward a simple need to count, to stop guessing what might be out there and start measuring how much starlight the sky actually contains. In the late 18th century, William Herschel and his sister Caroline set themselves a task that sounds almost impossible in its simplicity. They would try to turn the sky into data, not by sketching constellations, not by telling stories about the stars, but by using a telescope as a kind of sampling tool. Point it in one direction, count every star you can see in its field, then move, and do it again. Repeat, patiently, until the pattern of those numbers begins to sketch the shape of the system we live inside. At the heart of this project was an idea so modest it is easy to miss its ambition. If you assume that, on average, stars are distributed through space with a reasonably uniform density, then the number of stars you see in a given direction tells you something about how far your view extends. A shallow cone of vision contains fewer stars. A deeper cone, reaching farther into the galaxy, contains more. By counting stars in different directions, you can begin to infer where the stellar system is thick and where it is thin. Herschel did not try to count the whole sky at once. Instead, he divided it into many narrow strips and swept each one with his telescope, letting Earth's rotation carry new regions into view. In what he called his star gauges, he and Caroline carefully tallied the stars visible in each field. Altogether, he carried out these counts in more than 600 different directions, each one a small numerical probe into the Milky Way. From these measurements, he constructed one of the first quantitative maps of our galaxy. On paper, the Milky Way became a flattened, disk-like system of stars, somewhat longer than it is thick, with the Sun not exactly at the center, but not far from it. It is a strangely rough drawing by modern standards, more like a silhouette than a detailed chart. Yet in his time, it was a leap, the first serious attempt to see the overall shape of our stellar home from the inside. This is where the human element quietly re-enters, night after night. While most people slept under the same vague band of light across the sky, Herschel and his sister were turning that band into a graph. The work was repetitive, physically tiring, and intellectually demanding. It required faith that simple acts, looking, counting, recording could reveal a structure that no one had ever seen as a whole. To do this, he needed instruments that went beyond the modest lenses of ordinary telescopes. Herschel was not only an observer, he was a builder. In his workshop, he cast and ground mirrors, experimenting with sizes and designs to gather more light than the unaided eye could ever hope to collect. Eventually, his ambition led him to construct a vast reflecting telescope with a primary mirror about 48 inches across and a focal length of around 40 feet, the largest instrument of its kind in the world for roughly half a century. Standing on a high platform beside such a machine, looking into a field of view that contained countless faint stars, must have felt like leaning over the edge of a well whose bottom you could not see. The telescope did not change the universe, but it altered the relationship between the sky and the human body, where the naked eye offered a thin scattering of bright points. The instrument revealed a crowded depth, stars upon stars, piled into the darkness like grains of sand. Caroline's role in this was not a footnote. She kept records, timed observations, and later, working from the notes, helped organize the results into catalogues. Together they extended the list of known nebulae, those faint, cloud-like patches of light whose true nature was still uncertain, from about 100 objects to roughly 2,500. Each entry was another mark on the growing map, another reminder that the sky held more structure than anyone had suspected. For a while, Herschel believed that his star-counting method had done something close to final. The pattern of numbers suggested a disc-shaped system with a certain thickness, and beyond that, a thinning out into near emptiness. If the stars were indeed spread uniformly, then the places where his counts dropped could be taken as edges. It was tempting to think he had traced the boundaries of the universe itself, seen from our later perspective. We know where this confidence failed. The method assumed that all stars were similar in brightness and that nothing obscured the more distant ones. In reality, interstellar dust dims and hides the light from faraway stars, and stars themselves come in a wide range of intrinsic luminosities. His cone of sight ran into a fog he could not see, and his map, impressive as it was, described not the full extent of the galaxy, but the region transparent to his instruments. Yet there is something deeply revealing in this mistake. Herschel's map shows how far disciplined observation can take you, and also how easily a method, however careful, can create an illusion of completeness. The darkness beyond his inferred disk looked like emptiness. It was, in fact, the limit of his reach. If you think about it, this is not just an astronomical story. We are always, in our own lives, constructing maps from partial data, mistaking the edges of what we can detect for the edges of what exists. The Herschels did this on a cosmic scale. With tall scaffolds and heavy mirrors and long nights of counting, we do it in quieter ways, with memories, habits, and the narrow beams of attention we sweep across our days. Even so, what they achieved changed the conversation about the sky. Before their work, the Milky Way was mainly a visual impression, a soft band whose nature was open to metaphor. After their star gauges, it became a structure, a system of stars with a measurable thickness, a shape that could be sketched from the inside using numbers. The night sky was no longer just a backdrop. It was something you could survey, and that survey deepened the tension at the heart of the night sky paradox. Herschel's counts showed that stars are indeed more concentrated in the plane of the Milky Way than away from it, hinting at a disk-like form. But they also revealed that, even in directions of high density, the sky does not blaze with continuous light. There are always gaps, always patches where the counts thin, always a hint that something, whether dust, distance, or time, is limiting what reaches us. Standing at the eyepiece of his great instruments, recording star after star, Herschel thought he was, in some sense, seeing the universe as it is. We now know he was seeing the universe as filtered by the tools, assumptions, and wavelengths available to him. That does not diminish his work. If anything, it sharpens its meaning. His first cosmic map was not a final answer, but a step in a longer process, a demonstration that even when you see further than anyone before you, the darkness still has more to say. The first map of stars raised an uncomfortable follow-up. If our instruments keep revealing more, how can we be sure we have seen enough to say what the universe really is? Even while Herschel was counting stars, he kept encountering objects that did not resolve cleanly into points. Some looked like smudges, small patches of haze against the dark. Others showed loops, knots, or faint spirals when seen through larger telescopes. These were the nebulae, clouds in the sky whose true nature refused to settle to the naked eye. The most famous of them, the Orion Nebula, is only a blurred glow hanging like a ghostly star in the sword of Orion. Through a telescope, it opens into billowing structure, lit from within by young, hot suns. Modern measurements place it at a distance of about 1,344 light-years from Earth, close enough to be our nearest large stellar nursery, yet still far beyond anything we could ever reach directly. For astronomers of the 18th and 19th centuries, nebulae sat at the edge of understanding. Some clearly belonged inside our galaxy, glowing gas, star clusters, fragments of the Milky Way's own structure. Others, especially the faint, concentrated patches with hints of spiral arms, seemed different. They looked almost like miniature versions of the entire Milky Way, seen from far away. Were they small clouds nearby, or enormous systems far beyond our own? The question was not just about classification. It was about the size of reality itself. If the spiral nebulae were relatively small objects embedded in the Milky Way, then Herschel's map, with some corrections, might still capture most of what exists. If, instead, they were island universes, separate galaxies like our own at great distances, then the cosmos was vastly larger than even the boldest star counters had imagined. Observers did what they could with the tools they had. Larger telescopes revealed more detail. In the 19th century, William Parsons, using the huge Leviathan telescope in Ireland, drew intricate spirals in objects like the Whirlpool Nebula, suggesting structure far too organized to be a simple gas cloud. At the same time, other nebulae resolved into dense star clusters when seen more clearly, reinforcing the idea that at least some of these hazy forms were made of countless suns. But there was a limit no instrument could easily cross: distance. Without a way to measure how far away a nebula was, astronomers were left with shapes on the sky and guesses about scale. A small, nearby object can cast the same pattern of light onto our telescopes as a huge, distant one. Without a reliable standard candle, some object whose true brightness is known, it is almost impossible to tell the difference. Catalogues multiplied. Building on Herschel's work, astronomers compiled lists of nebulae and clusters. By the early 19th century, William Herschel's own catalogue included about 2,500 such objects, gathered over years of scanning. Later, toward the end of that century, John Louis Emile Dreyer assembled the new General Catalogue, bringing together observations into a list of 7,840 deep sky objects, galaxies, clusters, and nebulae of many kinds. On paper, the sky was becoming crowded. On the eyepiece, it still looked quiet. Most people, looking up unaided, saw the same scattered stars and dark gaps as their ancestors. The richness was hiding in the thin cone of a telescope's field, in small, concentrated patches of interest that only revealed themselves when carefully sought. This introduced a subtle new suspicion. If the universe can hide so much structure in places that look empty to the eye, what else might be present that no instrument has yet revealed? Each new catalogue, with its thousands of entries, was both a triumph and a reminder. These are only the objects we have noticed so far. I thank Thrive. The nebulae became symbols of this uncertainty. Some clearly belong to our own galaxy. Others did not fit comfortably anywhere. Spectroscopy, the study of how objects spread light into colors, began to offer clues. Emission nebulae showed bright lines, signatures of glowing gas. Many spiral nebulae, however, showed spectra more like those of collections of stars. They were not simply clouds. They were composite systems. Still, the decisive step was missing. Without actual distances, the debate could not be settled. Two maps of the universe coexisted uneasily in the same sky. In one, the Milky Way was nearly everything, a great system sprinkled with a few internal clouds. In the other, it was one island among many, surrounded by a vast ocean of similar structures. Caught in the middle, human beings kept doing what they always do when faced with scales that resist imagination. They continued to refine their methods, one small improvement at a time. Better mirrors reduced distortions. Longer exposures on photographic plates recorded faint details the human eye could not hold. New observatories were built on higher, darker sites to escape the blur and glow of the atmosphere below. And in the quiet between those technical advances, a more personal unease settled in. If a hazy blur in the eyepiece can turn out to be a galaxy containing hundreds of billions of stars, what does that say about our ability to judge importance by appearance alone? If something so enormous can hide behind a small smudge of light, how many of our conclusions in science, in life, are built on surfaces that later turn out to be disguises? The nebulae problem, at its core, was a question about completeness. When you look at the sky, are you seeing the universe as it mostly is, with only minor details missing? Or are you seeing a thin, local layer, with the true depth still largely concealed? The answer depended on those cloudy shapes, on whether they were mere decorative features of our own galaxy or markers of a far larger architecture. For decades, the evidence remained ambiguous. Each new observation seemed to whisper, almost, but not yet. The spiral forms hinted at grandeur. The star-like spectra pointed to composite systems. The growing catalogues suggested that such objects were not rare exceptions, but common features of the sky. Yet the final step, measuring their staggering distances, lay just beyond reach. In that gap between hint and proof, the night remained what it had long been, a mixture of certainty and doubt. Stars with known positions, nebulae with unknown scales, maps with carefully inked boundaries, and smudges at the edges where the ink fades. The universe was offering more clues than ever before, and at the same time, reminding anyone who looked closely that maps are not territory, and that seeing something is not the same as knowing where, or what, it truly is. Maps on paper could not answer the question by themselves. To know whether the universe really stretched beyond what we had drawn, astronomers needed something gentler and harder to obtain than any new telescope, a way to turn the sky into geometry. One of the simplest tools for that geometry is something you use without thinking every day: parallax. Hold up a finger in front of your eyes. Close one eye, then the other. The finger seems to jump against the background. Your brain quietly uses that shift to judge distance. Two viewpoints, one object, and a triangle formed in your head. Now stretch that idea outward. Earth moves around the sun. That orbit provides two viewpoints, separated by a vast baseline. When Earth is on one side of its orbit, we look at a nearby star against the distant background. About half a year later, when Earth has moved to the opposite side, we look again. The apparent position of the nearby star has shifted by a tiny angle. That shift is stellar parallax. The baseline between those two positions is about 2 astronomical units. Since 1 astronomical unit is the average distance between Earth and the Sun, roughly 150 million kilometers across, the angles involved are unimaginably small. For the closest stars, the apparent wobble is a fraction of an arcsecond, where 1 arcsecond is 1/60th of 1 arcminute, and 1 arcminute is 1/60th of a degree. Try to picture that. A full circle around you is 360 degrees. Each degree is sliced into 60, and each of those slices into 60 again. Parallax asks you to measure a deflection smaller than one of those final slivers. For centuries, no one could do it. Telescopes were not precise enough, mounts were not stable enough, and the atmosphere above blurred the light. The absence of observed parallax was even used as an argument against the idea that Earth moves. If Earth really orbited the Sun, people asked, why did the stars not show the expected shift? The answer, though not yet provable, was that the stars had to be far farther away than anyone had imagined. The triangle was simply too skinny for the angle at its tip to be resolved. In the early 19th century, that changed. Friedrich Bessel chose a faint double star in the constellation Cygnus, a system now known as 61 Cygni, and devoted years of meticulous observation to it. In the year written as 1838, he announced that he had detected its parallax, and from that, inferred its distance. The value he derived corresponds to about 11 and a little more than 4/10 light years from Earth. remarkably close to the modern figure. For the first time, a star other than the Sun had been given a measured distance, not an estimate based on brightness, not a guess, but a number derived from geometry. The universe acquired depth. The night sky was no longer a flat pattern. It became a three-dimensional arrangement with at least one known point. The method has a built-in unit. If a star shows a parallax angle of 1 arcsecond when observed from Earth, its distance is defined as 1 parsec, which works out to a little more than 3 and about 1/4 light years. Most nearby stars have parallaxes smaller than that, meaning they sit at multiple parsecs, their angles even tinier, their distances even larger. Parallax seems straightforward on paper, but it collides directly with our limits. The further away a star is, the smaller its parallax angle becomes. Eventually, the shift is so slight that it drowns in the noise of imperfect instruments and atmospheric turbulence. For a long time, only the very nearest stars could be measured this way. The cosmic map extended a little beyond the Sun, then faded back into uncertainty. Later, space observatories changed that. Freed from the blurring air, instruments like the Hipparcos satellite, and then the Gaia mission, could measure angles far beyond what ground-based telescopes could manage. Gaia, in particular, is designed to reach accuracies of order 10 microarcseconds for many stars, fine enough to map distances for stars across tens of thousands of light years in our galaxy. Even so, parallax remains a local tool on the scale of the entire universe. It builds a reliable foundation, but beyond that foundation, other methods must take over. There is a quiet lesson hiding here. To measure the distance to a star with parallax, you need 2 separated vantage points and a willingness to accept that the triangle you are constructing is extremely skinny. The method does not make the universe smaller or more comfortable. It simply tells you exactly how far away the nearest lights are, and how insignificant even those distances can make you feel. Yet the fragility of the method is part of its meaning. Bessel's result, that first successful stellar parallax, depended on millimeter shifts on his measuring scales, on patient repetition, on sleepless nights, checking and rechecking tiny deflections. A vast 11 light-year gulf reduced to a fraction of an arcsecond on paper. The cosmos is enormous. The evidence for its scale is written in the tiniest of angles. In everyday life, we rarely confront the fact that our own judgments of distance and importance are built on similar triangles. We view events from one position, then from another, and from the discrepancy we infer depth. Parallax becomes not just a technique in astronomy, but a quiet metaphor for perspective itself. Change your baseline, even slightly, and the pattern can shift. Still, no matter how sensitive our instruments become, there will always be stars whose parallaxes are too small to measure directly, galaxies too distant for this geometric trick to reach. Beyond a certain range, the universe once again flattens out in our data, not because it lacks depth, but because our baseline, the orbit of our small planet around its star, is fixed. We are measuring the immeasurable with a ruler whose length is set by where we happen to live. So parallax sits at an edge. On one side, it anchors our understanding of distance in something tangible and repeatable. On the other, it reminds us that even our best tools have horizons. Between those horizons and the infinite structures we imagine lies a gap that no telescope can fully erase. The night sky paradox emerges, in part, from that gap. A universe that might be infinite, a method that is not, and a darkness that records the difference. Parallax had given the universe a first layer of depth, but beyond that shallow shell, distances blurred again. At some point, geometry alone was not enough. The sky needed a different kind of ruler. At the Harvard College Observatory, around the turn of the 20th century, that new ruler was being carved in silence. In a brick building in Cambridge, Rows of women sat at long tables, examining photographic plates through magnifying lenses. They were called computers. Their job was to turn specks of light into numbers. One of them was Henrietta Leavitt. Leavitt had joined the observatory as a volunteer in the year 1895 and later became part of the permanent staff. She did not spend her nights at the telescope. Instead, glass plates exposed by others were brought to her desk. Each plate, a frozen image of some region of the sky. She compared them, plate against plate, looking for stars that changed. The region that would change everything for her, and for us, was the small Magellanic Cloud, a faint, irregular patch of light in the southern sky. Today we know it is a dwarf galaxy, orbiting our own at a distance of roughly 200,000 light-years, one of our nearest extragalactic neighbors. On the plates, though, it was a crowded swarm of tiny marks, each one a star whose distance, at the time, no one could measure directly. Leavitt was not looking for beauty, she was looking for rhythm. Night after night, using a blinking device that let her flip rapidly between plates taken at different times, she watched for stars that brightened and dimmed. Over the years, she identified thousands of variables in the Magellanic Clouds. In the large Magellanic Cloud alone, she catalogued about 2,000 variable stars, of which only about 20 turned out to be of a particular type. Those few were Cepheid variable. To the eye, a Cepheid looks like an ordinary star, but if you plot its brightness over time, a pattern emerges. The light rises, often quite quickly, reaches a peak, then falls more slowly, and repeats. Each star has its own period, a time between one maximum and the next, which can range from about 1 day to roughly 100 days or more, depending on its physical properties. The key feature is not just that they vary, it is that they do so regularly. Leavitt's insight was both simple and radical. In the small Magellanic Cloud, she reasoned, all the stars were roughly at the same distance from us. Compared with their separation from each other, that meant that differences in the apparent brightness of stars there could not be blamed mainly on some being much farther away than others. Those differences had to be, at least in large part, intrinsic. By measuring the periods of Cepheid variables in that galaxy and comparing them with their average brightness on the plates, she noticed a pattern. The longer the period of the star's pulsation, the brighter the star truly was. In her famous work, published in the year 1912, she plotted this relation clearly, using a sample of 25 Cepheid variables in the small Magellanic Cloud. This connection between period and luminosity is now often called the Leavitt law. It transforms Cepheids into standard candles. If you know that a given Cepheid's brightness rhythm corresponds to a specific true luminosity, you can compare that true luminosity to how bright it appears from Earth. From that comparison, through the inverse square law of light, you can infer its distance. In other words, Leavitt had uncovered a way to turn time into distance. There is a quiet, almost fragile power in that, instead of relying on huge triangles like parallax, with baselines measured in astronomical units, she was listening to the internal heartbeat of stars. The universe was offering a Morse code of light and darkness, and she found a pattern in its timing. At first, the scale was still uncertain. Her relation was beautifully shaped, but it floated without a firm anchor, because the absolute distance to the Magellanic Clouds was not yet known. She could say that a Cepheid with twice the period was intrinsically brighter than one with half the period, but not precisely how far away either star was in kilometers or light years. That calibration would come later, when other astronomers, like Ejnar Hertzsprung, and later many others, used parallax for a handful of nearby Cepheids and then stretched Leavitt's law outward. Even without that calibration, something profound had changed. The cosmos had offered us a link between how a star changes in time and how bright it truly is in space. It was as if some distant lighthouse were not only flashing, but flashing in a way that quietly told you how strong its bulb was. From a personal angle, the scene is almost stark. A woman, working in a low-paid position, excluded from the telescopes and the prestige they carried, sits over glass plates under artificial light, drawing dots and numbers in notebooks. She does not travel to observatories on mountaintops. She rarely appears in the grand debates of the time. Yet the line she draws between period and luminosity becomes one of the main supports of the cosmic distance ladder. Our understanding of the vast scale beyond the Milky Way, of the true size of the universe we inhabit, depends on this patient work. Long after the glass plates yellowed and the ink faded, others would take her relation, refine it, and use it with larger and larger telescopes. When Edwin Hubble identified a Cepheid variable in the Andromeda Nebula and used its period to estimate its distance, showing that Andromeda lay far outside the Milky Way, he was standing directly on Leavitt's foundation. In that sense, the universe's expansion, the recognition that galaxies are racing away from each other on cosmic scales, is not just a story about redshifts and spectra. It is also a story about someone quietly noticing that certain stars blink with a rhythm that reveals how far away they must be. There is a deeper tension here, too. The night sky paradox tells us that, in a universe filled everywhere and everywhen with stars, the sky should be overwhelmingly bright. Leavitt's work, by making it possible to measure distances to those stars and to the galaxies they inhabit, begins to show us that the real universe does not behave that way. There is a finite number of stars within any given observable volume. Their light is limited. It has taken a finite time to travel. As we extend the Leavitt law outward, we begin to see that galaxies are not painted on a single shell, but scattered through an expanding space. The darkness between them is not just an absence. It carries the imprint of the fact that light has not had infinite time to accumulate. And still, at the core of that whole chain, is a person watching tiny changes in black and white smudges on glass. It is hard not to feel a kind of double perspective here. On one side, the universe revealed by Leavitt's relation is vast beyond intuition. The small Magellanic Cloud, already unimaginably distant, is only a nearby satellite in a much larger structure. Thousands of galaxies, each containing hundreds of billions of stars, populate the observable cosmos. On the other side, our access to all of that depends on very human scales, fractions of a magnitude on a plate, careful handwriting in a notebook, the decision to persist in looking for patterns where others might only see noise. If you step outside on a clear night and look up, you do not see Cepheids as such. You see points of light, some of which may, in reality, be stars that swell and dim with steady periods measured in days and weeks. You see the integrated result of a universe in motion. The fact that we can now attach distances to some of those points, that we can say, with some confidence, how far away the nearest galaxies lie, is inseparable from the work Leavitt did at her desk. In the story of Why the Night is Dark, she occupies a quiet but crucial place. By teaching us how to measure cosmic distance far beyond the reach of parallax, she helped us build a three-dimensional map of where the light is. That map, in turn, makes the missing light speak. To understand why the darkness is there, we first had to learn, patiently and humbly, how far the nearest islands of brightness really are. Those islands of brightness would not stay still for long. Once we knew how far away they were, the next quiet question was inevitable. If we measure them again and again, are they moving? On a mountain above Los Angeles, Edwin Hubble spent his nights staring at small, gray smudges of light that most people would never notice. At Mount Wilson Observatory, he worked with the Hooker telescope, a reflecting instrument whose primary mirror was about 100 inches across, the largest in the world at the time. Through that glass, the sky lost some of its softness. The hazy nebulae became textured. Stars separated. Shapes emerged. One of those smudges was Andromeda, a faint, elongated glow that had been catalogued, debated, and misunderstood for centuries. Some thought it was a kind of cloud inside the Milky Way. Others suspected it might be an entire stellar system of its own, far beyond our own galaxy. The arguments were passionate, but they all suffered from the same wound: no reliable distance. Hubble approached Andromeda with a new tool in mind. He knew of Henrietta Leavitt's work on Cepheid variables, of the way their pulsation periods could reveal their true brightness. So he did something deceptively simple. He patiently took photographic plates of the Andromeda Nebula over time and examined them for stars that blinked with a regular rhythm. On one plate, he marked a tiny point of light with a small letter, then crossed it out and wrote another beside it, var, for variable. It was a Cepheid. By measuring its period and using Leavitt's relation, he could estimate its intrinsic luminosity, then compare that to how faint it appeared. From that comparison, he derived a distance for Andromeda of about 900,000 light-years, far larger than the size then attributed to the Milky Way. Even though that value was still too small by modern standards, it was already enough to break the old picture. Andromeda could not be a little cloud inside our galaxy. It was a separate system, an island universe in its own right. Later refinements would place it at roughly 2.5 million light-years away, with more precise work giving a distance of about 2,480,000 light-years. But the crucial step had been taken. The universe had abruptly grown from a single galaxy to a vast archipelago. Once that door opened, the nebulae problem shifted. Those faint spirals and patches were no longer odd features within a single structure. They were other galaxies, scattered through space. Each one contained hundreds of billions of stars. Each one, when viewed from far enough away, would resemble the Milky Way, the night sky. In this new view, was not just sprinkled with stars, it was sprinkled with entire cities of stars. At the same time, other astronomers had been measuring something subtler in the light from those galaxies. When you pass starlight through a prism or a grating, it spreads into a spectrum, a band of colors crossed by dark or bright lines. Those lines are fingerprints of the elements in the star's atmosphere. For some of the nebulae, the positions of these lines were shifted toward the red end of the spectrum. Vesto Slipher, in particular, had spent years before Hubble's distance work carefully measuring these redshifts, finding that many spiral nebulae seemed to be receding from us at high speeds. Hubble saw a chance to connect two kinds of information: how far away a galaxy is, and how fast it seems to be moving along the line of sight. Using Leavitt's Cepheid method for distances in a handful of nearby galaxies, and combining those with redshift measurements gathered by himself and colleagues like Milton Humason, he plotted recessional velocity against distance. The pattern was rough, noisy, but unmistakable. On average, the more distant a galaxy was, the faster it appeared to be receding. In a paper published in the late 1920s, he described a simple relation. The recessional speed of a galaxy is roughly proportional to its distance from us. The constant of proportionality, now called the Hubble constant, he estimated to be on the order of 500 kilometers per second for every megaparsec of distance. The exact value would later be revised downward as distance measurements improved. But the core insight remained. The universe was not static. On large scales, it was expanding. This expansion is easy to misunderstand. It does not mean that galaxies are racing through a pre-existing space like shrapnel from an explosion in air. Instead, the space between galaxies is stretching, A common image is a loaf of raisin bread rising in an oven. The raisins represent galaxies. As the dough expands, each raisin sees the others move away. The farther another raisin is, the faster it seems to recede, simply because there is more dough between them being stretched. In this picture, no galaxy sits at a special center. Every observer, wherever they are, sees distant galaxies moving away on average, with farther ones receding more quickly. It is a deeply democratic universe, at least in geometry. Our Milky Way is not privileged. It is one raisin among many. There is a quiet shock in realizing this. The night sky, which once felt like a static tapestry, becomes a frame from a film in motion. All the stars and galaxies you see are part of a pattern that is changing, not in the dramatic way of explosions, but in the slow, inexorable way that distances lengthen over cosmic time. If you take this expansion seriously and run it backward in your mind, something remarkable happens. Galaxies that are now widely separated move closer together. The dough of space itself shrinks. At earlier times, everything was more compressed. Follow that logic far enough, and you arrive at a state where the densities and temperatures must have been far higher, a universe younger and hotter than anything we can directly observe now. Hubble himself did not fully embrace all the implications. The idea that the universe might have had a beginning in time, a finite age, was unsettling to many. A static, eternal cosmos felt safer. It is ironic, the data he helped produce would become some of the strongest evidence against that static picture. And yet he often spoke cautiously about the interpretation. Others, like Georges Lemaitre, a Belgian priest and physicist, saw more clearly that an expanding universe naturally suggests an origin. Lemaitre had, in fact, derived a version of the distance-velocity relation theoretically before Hubble's empirical law was widely known, and proposed that the universe might have started from what he called a primeval atom. The details of that early state would be worked out later, but the basic conclusion linked directly back to the dark night sky. If the universe has a finite age, then light has only had a finite time to travel. In such a universe, even if space might be infinite in extent, only a finite region is observable. Light from beyond a certain distance has simply not reached us yet. There has not been enough time. Combine that with the redshifting and cooling of light as space expands, and you begin to see how the night can remain dark even in a cosmos filled with luminous matter. Hubble's work did not solve the night sky paradox by itself, but it changed the terms of the problem. The assumptions that made the paradox so sharp and eternal, unchanging universe, were no longer tenable. Instead, we had a universe with a history. A universe in which the arrangement of galaxies today is one frame in a long sequence. There is another, quieter strand running through this story. The distance scale of the universe, the fact that Andromeda is millions of light years away, that galaxies recede at thousands of kilometers per second, that the observable cosmos stretches over tens of billions of light years. All of that passes through the hands of individual people standing in specific places, at specific times, on a small planet. Hubble, walking up the mountain road, Leavitt bent over glass plates, Slipher watching faint spectral lines drift in his spectrograph. None of them saw the whole. Each had a narrow task, a particular measurement. Yet together they revealed that space itself is stretching, that the universe is not a still stage but an unfolding process. On a clear night now, if you find Andromeda as a faint smudge above the horizon, you are looking at a galaxy whose light has been traveling for a couple of million years to reach you, a system moving toward us even as the universe on larger scales expands. The photons entering your eye began their journey long before any human language, long before any questions about expansion or origins. They carry, folded into their wavelengths, the imprint of a universe that has been stretching for most of its own lifetime. The paradox of the dark night sky started as a simple clash between intuition and observation. With Hubble's work, that clash became part of a larger narrative. Darkness is no longer a trivial backdrop. It is a consequence of a universe with a finite age, a dynamic geometry, and a horizon beyond which light has not yet arrived. And the fact that we can say that at all, from here, from this quiet, a local corner of a single galaxy, is its own kind of astonishment. The moment you say that the universe is expanding, another question slips in underneath it. If everything is moving apart, then what exactly is it that is stretching? We normally treat space as background, a room, a stage, an empty container that things sit in. You move the furniture, not the room. Planets orbit the sun inside a kind of invisible box. Galaxies drift through a vast, hollow volume. In everyday thinking, space is nothing more than the gap between objects. Physics has not always agreed on that. In the late 17th century, when Isaac Newton published his great work on motion and gravity, he treated space as something absolute, a real, fixed arena that exists whether or not anything occupies it. In that view, you can imagine the universe completely empty. No stars, no planets, no dust, and still say that there is space there. It has directions. It has distances. It is like a perfectly built stage waiting for actors. The advantage of this picture is its clarity. If space is absolute, then you can talk about true rest and true motion. You can, at least in principle, say whether something is really rotating or just sitting still, regardless of what anything else is doing. Newton even used a spinning bucket of water as an example. The curved surface of the water, he argued, showed that the bucket was rotating relative to space itself, not just relative to other objects. Opposing this, thinkers like Gottfried Wilhelm Leibniz argued for a different idea. For them, space was not a thing in its own right. It was a way of talking about relationships. Distances and directions only make sense between objects. Remove all the matter, and there is nothing left to label. In that relational view, there is no such thing as the position of a lone particle in empty space. There are only patterns of separation among many particles. This debate may sound abstract, but it quietly touches the way we talk about the night sky. When you say that stars are far apart, you are using space as a measuring concept. When you imagine the universe expanding into something, you are smuggling in the idea of a larger container outside the one we occupy. The question, what is space, really sits behind all of this. Modern physics did not settle the argument with a simple vote. Instead, it transformed it. In the early 20th century, Albert Einstein developed the general theory of relativity, published around the middle of the 19-teens, which describes gravity not as a force acting across a static emptiness, but as the curvature of space and time woven together. In that framework, space is not a rigid box. It can stretch, bend, and ripple. Light follows the curves of this geometry. Planets move along paths shaped by it. There is no fixed grid behind the scenes. The grid itself is part of the story. At the same time, general relativity still treats the geometry as something that can exist even where matter is absent. You can write down a description of empty space that is curved or flat, with or without gravitational waves passing through it. In that sense, Newton's instinct that there is a real structure there, even when no objects are present, survives in a more subtle form. Things become even stranger when you add quantum physics. In quantum field theory, the vacuum is not truly empty. It is the lowest energy state of fields that fill all of space. Those fields can fluctuate. Particles can briefly appear and vanish. The vacuum has properties, an energy density, a tendency to polarize in electric and magnetic fields, a capacity to influence how particles move. Empty space begins to look less like nothing and more like a medium with its own behavior. And yet, on human scales, we keep experiencing space as absence. You look up at the sky, and most of what you see is black. The stars are real. The galaxies are real. But between them, there is a vast reach of something that feels like nothing. The fact that we can assign a speed to light about 300,000 kilometers each second in vacuum only emphasizes how featureless that medium seems. Light does not speed up or slow down in empty space. It simply moves. Cosmology adds another layer. When we say the observable universe has a radius of roughly 46.5 billion light-years, we are not just describing where matter happens to be. We are describing the region of space-time from which light has had time to reach us since the universe became transparent. Beyond that radius, things may exist, but they are, for now, outside our light cone. They cannot have influenced us yet, not even by sending a single photon. This introduces a subtle shift in how we think about where we are. We are not just in a place, we are in a region of causal contact, a bubble defined by what has had time to reach us. Space, in this sense, is not only geometry, it is also a record of what can touch what, and when. If you sit with that, the question, what is space, starts to sound less like, what is the container, and more like, what are the rules that connect events? Separated by millions of light years, might be linked by the light they send across the dark. A fluctuation in the early universe can leave imprints stretched across the cosmic microwave background. Your own existence is tied to a specific world line, a path through space-time that can intersect some events and forever miss others. The night-sky paradox came from imagining an infinite, eternal space filled uniformly with stars. In that picture, space is a passive backdrop. The paradox dissolves when we acknowledge that space is dynamic, that it has a history, that distances between faraway galaxies grow with time. Darkness is not just where stars are missing. It is where space-time itself has not yet delivered their light to us, or has stretched that light beyond the range of our eyes. Philosophers of physics sometimes ask whether space-time is emergent, whether the smooth continuum we describe in our theories might be a large-scale approximation to something more granular underneath, the way a fluid is made of molecules. If that is true, then the blackness between the stars is not a featureless void, but the averaged behavior of deeper degrees of freedom we do not yet see. But even without chasing those speculations, our everyday understanding already has to bend. Saying that space is nothing does not fit what our best theories tell us. Saying that it is a thing, like a material object, is also misleading. It is better to think of it as a network of possible relations, where light can travel, how long it takes, which events can influence which others. From that perspective, the dark night sky is part of the structure. The black regions are not empty slots waiting to be filled. They are stretches of space-time where, for now, the rules connecting us to distant matter have simply not had enough time to complete their work, or have redshifted the arriving light into wavelengths our eyes cannot detect. None of this answers, in any final sense, what space really is. The question keeps slipping away as soon as you try to pin it down. What the history of physics does show is that every time we treat the backdrop as simple, it eventually resists. Newton's absolute stage was challenged. Leibniz's pure relations were not the whole story. Einstein's curved space-time may itself be an approximation to something deeper. And still, the experience remains very simple. You step outside at night, you look up. There is the dome of the sky, which you know is not a dome. There are scattered points of light, which you know are suns and galaxies. Between them, there is darkness, which you now know is not just an absence, but the visible shape of the limits of connection. Space, in that moment, is not an abstract set of coordinates or a line in an equation. It is the quiet distance between you and everything else. It is the fact that some things can reach you with their light and others, for now, cannot. It is the invisible fabric that makes the night sky paradox possible in the first place, and, slowly, allows us to understand why that paradox exists at all. Once you start to see space as something with rules of its own, another unsettling idea follows. What if the rules you grew up with are only local? From childhood, most of us are trained in a very particular kind of geometry. It lives on flat pages and classroom blackboards. Straight lines never bend. Parallel lines, once set side by side, stay the same distance apart forever. The angles inside any triangle add up to a neat, satisfying total. On that flat world, the sum of the interior angles of every triangle is exactly 180 degrees. This version of geometry feels obvious. It fits what we see on tables, floors, walls. It is baked into rulers and set squares and the way we draw maps. For a long time, it was simply called geometry. Full stop. The idea that it might not apply everywhere did not just seem wrong. It barely seemed meaningful. The first cracks appear when you step off the page and onto a sphere. Imagine the surface of Earth, smoothed out, with mountains and oceans ignored. Its average radius is about 6,371 kilometers, a size that has been measured and checked in many independent ways. For most everyday purposes, that surface is curved so gently that a small patch looks flat. A football field, a city street, even an entire country can be treated as if it lay on a plane. But now draw a triangle using only the shortest possible paths on that spherical surface. Start at the North Pole. Walk straight down a line of longitude until you reach the equator. Turn 90 degrees and walk along the equator for a quarter of the way around the planet. Turn 90 degrees again and walk back up another line of longitude to the pole. You have just drawn a triangle whose three interior angles are all right angles. 90 degrees at the equator where you turned, another 90 where you turned again, and a full 90 at the pole where the lines of longitude meet. 3 right angles add up to 270 degrees, not 180. Nothing went wrong with your walking. Your straight lines on the sphere are the natural shortest paths, called great circles. What failed was your expectation that triangle angles must always sum to the same value. On a sphere, they do not. In fact, the sum of the angles of any triangle on a sphere is always greater than 180 degrees and always less than 540 degrees. The rule you learned in school was never universal. It was a special case for nearly flat regions of a much larger, gently curved surface. Once you accept that, a door opens. You can imagine other kinds of surfaces, where the familiar rules break in different ways. Saddle shapes, where triangles have angle sums less than 180 degrees, or more exotic constructions where straight lines, defined as locally shortest paths, spread apart or converge in unfamiliar patterns. Geometry, it turns out, is not about the shapes drawn on space, but about the properties of space itself. Mathematicians like Carl Friedrich Gauss and Bernhard Riemann made this precise. They showed that you can define the geometry of a surface entirely from within, without ever stepping outside to look at it from a higher dimension. A two-dimensional being living on the surface of a sphere could, in principle, discover that its world is curved by measuring distances and angles, without ever seeing the sphere from space. One of Gauss's key insights was that curvature can be detected by purely internal measurements. If you walk around a closed loop and keep track of how your direction changes, the net twist you accumulate encodes information about the curvature of the space you are in. No external embedding is needed. Geometry is not imposed from the outside, it is woven into the inside. Riemann went further. He generalized these ideas to spaces of any dimension, defining what we now call a metric, a rule that tells you how to compute distances between nearby points, which in turn determines angles, areas, volumes, and the paths of straightest motion. In his framework, you can have a three-dimensional space where the rules of distance differ from those of ordinary Euclidean space, or a four-dimensional space-time with its own peculiar structure. At first, this may feel like a game of imagination. Strange triangles, odd sums of angles, curved surfaces you cannot easily visualize. But Riemann's abstract mathematics turned out to be exactly what Einstein needed when he tried to describe gravity not as a force, but as geometry. In general relativity, the presence of mass and energy tells space-time how to curve, and that curvature tells matter and light how to move. This is not a slogan, it is a precise statement written in Riemann's language. The metric of space-time is no longer fixed and flat. It is dynamic, responding to the distribution of matter. Light, which always follows the locally straightest possible path in this geometry, can appear to bend when it passes near a massive object, not because a force is pulling it sideways, but because the space it is traveling through is curved. Einstein's theory predicted that light skimming past the sun would be deflected by about 1 3/4 of an arcsecond, a tiny angle that was later confirmed during a solar eclipse in the early 20th century. An arcsecond is a fragile unit. It is 1/3600th of 1 degree. 1 3/4 of such a sliver is an almost unimaginably small deflection to try to measure on the sky. Yet that small kink in the path of starlight carries the weight of a very large idea, that the geometry of space near the sun is not Euclidean. The straightest possible line in that region is not what you would draw on a flat sheet. This is where geometry truly begins to slip free of everyday intuition. On the scale of rooms and streets, the curvature of Earth is almost invisible. On the scale of the solar system, the curvature of space-time is subtle but measurable, bending light, shifting orbits, affecting the ticking of clocks. On the scale of the whole universe, that curvature might be positive, negative, or so close to zero that, within current measurement limits, it looks flat. You can think in terms of three broad possibilities. If the large-scale geometry of space is positively curved, like a higher dimensional analog of a sphere, then straight lines that start off parallel may eventually meet. Triangles drawn on immense scales would have angle sums greater than 180 degrees. A universe of this type could be finite in volume while having no edges, like the surface of Earth. If the geometry is negatively curved, like a saddle, straight lines that start off parallel drift apart. Triangles would have angle sums less than 180 degrees. Space would be infinite in extent, but its global structure would be very different from the flat case. If the curvature is exactly zero, then Euclidean rules hold on all scales. Triangles of any size would have angle sums of 180 degrees. Parallel lines would never meet and never diverge. Space would be infinite and flat. Measurements of the cosmic microwave background, the afterglow of the hot early universe, suggest that on the largest scales we can see, the geometry is extremely close to flat, though whether it is perfectly so or just very nearly is still an open question. Once again, observation and geometry intertwine. By analyzing tiny variations in that ancient light, we infer properties of the space it has traveled through for billions of years. All of this circles back to the simple picture of the night sky. When you look up, you are not looking at stars painted on the inside of a dome. You are looking along geodesics, the straightest available paths in a curved space-time whose properties you cannot directly feel. The distances between galaxies, the way light redshifts as it travels, the ultimate fate of cosmic expansion. all depend on that large-scale geometry. It is no longer enough to say that space is where things are. Space has become an active participant in the story. Its curvature influences how structures form, how light accumulates or fails to, how horizons appear. The darkness of the night sky is shaped not just by how many stars exist, but by the way the underlying geometry stretches and folds the paths their light must take to reach you. There is something quietly humbling in this. The rules you learn as a child about straight lines, flat surfaces, simple triangles are not wrong. They are local approximations, good within a small patch of a much stranger manifold. You grow up in a region of space-time that is nearly flat, and your intuition is trained accordingly. Only later, when you try to follow light across millions of light years, do you discover that intuition is provincial. Curved space is, in that sense, a new reality, not because it destroys the old one, but because it reveals its limited scope. The floor still supports you. The table is still flat enough to write on. The triangle in your notebook still has angle sums that are, for all practical purposes, 180 degrees. But above you, on scales your body will never traverse, the geometry bends. And in those bends, in those slight departures from flatness, the universe hides the explanation of why the night is not filled with light. If the rules of geometry can bend, then the stage you stand on is not as still as it feels. At some point, someone had to ask the unnerving question out loud. What if gravity is not a force at all, but a sign that space itself is moving? Einstein did not start from the sky. He started from something much closer, the feeling of weight. Imagine standing in a windowless elevator. If the cable snaps and the elevator falls freely, something strange happens. For a brief moment, as you drop, you feel weightless. Objects float beside you. A dropped key hovers. Inside that falling box, it is as if gravity has been switched off. Now imagine the same elevator far away from any planet, drifting in deep space. A rocket engine attached to its floor fires, pushing the elevator upward with constant acceleration. Inside, you feel pressed to the floor. Drop the key and it falls, just as it did on Earth. There is no difference, from your point of view, between standing in a gravitational field and standing in an accelerating box. This is the equivalence principle. Einstein's starting clue. Locally in a small enough region of space and time, you cannot tell the difference between being pulled by gravity and being pushed by acceleration. That simple idea ties together motion and weight in a way Newton's picture never did. If that is true, then the path of a freely falling object is not being pulled by a mysterious force. It is doing what things always do when left alone, following the straightest possible path. But straight, now, is defined not in a flat, featureless space, but in a curved space-time whose geometry we have to learn. Here is where Einstein reached for the tools Riemann had built. Space-time. In this picture is a four-dimensional fabric, 3 dimensions of space, 1 of time, all woven together. At every point, the metric tells you how to compute distances and durations. Curvature tells you how those distances and durations fit together over larger regions. Einstein's great insight was to write down equations that linked this curvature to the distribution of matter and energy. In compact form, they look dense and opaque, but their meaning can be phrased in words. The presence of matter and energy tells space-time how to curve, and that curvature tells matter and light how to move. A planet orbiting a star is not being tugged along by invisible strings. It is following a geodesic, the natural path in the curved geometry created by the star's mass. Light passing near that star bends for the same reason. It is not deflected by a force. It is tracing out the straightest available route in a space-time that is no longer flat. This shift is easy to state and hard to digest, because it demotes something we are used to treating as fundamental: gravity. which we experience intimately every day, becomes a symptom rather than a primary actor. What is fundamental is the geometry, an invisible structure we do not directly feel, but which shapes every motion we make. Einstein applied this framework not just to stars and planets, but to the universe as a whole. If matter curves space-time, then a cosmos filled with matter must have a global geometry. It cannot simply sit flat and unchanging. When he first wrote down the equations, though, the idea of a dynamic universe seemed too radical, even to him. So he made a choice he would later regret. He added an extra term to his equations, the cosmological constant, designed to counteract the mutual gravitational attraction of matter and to allow a static, unchanging universe to exist. Without that term, his equations naturally produced expanding or contracting solutions. With it, he could tune things so that the cosmos, on average, stayed the same size. On paper, the static universe worked, but only just. It was precariously balanced, like a pencil standing on its point. Any small disturbance would tip it into expansion or collapse. Around the same time, however, other physicists, Alexander Friedmann, and later Georges Lemaitre, found exact solutions to Einstein's equations that described universes which did expand or contract, driven by their own internal dynamics. When Hubble's observations of receding galaxies became widely known, the balance tipped. The universe we see is not static. On large scales, it is expanding. At that moment, Einstein's reluctance to let his equations say what they naturally wanted to say became obvious. He is said to have called the introduction of the cosmological constant his greatest blunder, though modern cosmology has quietly resurrected that term in a different role. From the point of view of the night sky paradox, what matters is this. In Einstein's universe, space is not a neutral container. It can stretch. It can carry waves. It can have a history. It can, in principle, begin. Gravitational waves are a clear example of this liveliness. When massive objects like black holes orbit one another and merge, they disturb spacetime itself. Those disturbances travel outward as ripples, compressing and stretching distances as they pass. For a long time, they were a theoretical prediction, an almost poetic consequence of the equations. A century after Einstein wrote them down, experiments finally detected these waves directly, confirming that space-time can vibrate. In a more everyday sense, the expansion of the universe is also a kind of slow, large-scale wave. The metric that defines distances between galaxies changes over time. Light traveling through this expanding fabric is stretched, its wavelength lengthened, its color reddened. The cosmic microwave background, the faint afterglow of the hot early universe, started as radiation at much higher energies. As space expanded, that light cooled, becoming the almost uniform microwave hiss we see today. All of this means that when you ask why the night sky is not overwhelmingly bright, you are not just counting stars. You are also accounting for the way their light has been diluted and cooled by the expansion of the very medium it travels through. In a static, eternal universe, light would accumulate until the sky blazed. In a dynamic Einsteinian universe, with a finite age and a changing geometry, light does not have infinite time to pile up, and what does arrive has often been shifted into wavelengths our eyes cannot detect. There is a more personal undercurrent to this, which rarely appears in equations, but is hard to ignore. If space and time are part of a single fabric, then your life is a path laid out in that four-dimensional structure. You occupy a narrow tube in space-time, a world line that starts at your birth and ends at your death, woven through the larger web of events. From that line, you can see only a thin slice of the whole. Your present is a small cross-section. Your memories are traces of where you have been on that path. Your expectations are guesses about the parts of the universe your world line might intersect later. All the while, other paths weave around you, most never touching. Some crossing briefly, a few running parallel for a while, and then diverging. Einstein's universe does not offer comfort or purpose by itself. It does not tell you why your path takes the shape it does. What it does say, quietly and firmly, is that you are embedded in a structure that is larger and stranger than your senses suggest. The weight you feel in your legs, the falling of an apple, the orbit of the moon, the bending of light from distant galaxies, all of these are local expressions of a geometry shaped by matter and energy everywhere. In that setting, the night sky you see when you look up is not an external decoration. It is a cross-section of this curved space-time that happens to intersect your eyes here and now. Each photon that arrives has traveled along a geodesic, its path determined by the curvature along the way. Some paths are blocked by dust or gas. Some are stretched until their energy dwindles. Some have not had enough time, since the universe became transparent, to reach you at all. So the darkness between the stars is not simply where no light was ever produced. It is where, given the age and shape of the universe, no light has yet arrived, or where the light that did arrive has been shifted beyond the narrow band of wavelengths you can see. If, hypothetically, your eyes could detect microwaves, the night sky would not be black. It would glow faintly in every direction, with the chilled remnant of the early cosmos, Einstein's universe. Then, turns the paradox into a kind of diagnosis. The fact that the sky is dark, invisible light, but filled with a uniform microwave background tells you something very specific about the age, history, and geometry of everything. It tells you that there was a time when the universe was hot and dense, filled with radiation. It tells you that space has expanded by an enormous factor since then. It tells you that there is a cosmic horizon beyond which you cannot see, not because nothing lies there, but because space-time has not yet allowed its light to reach you. You live inside that diagnosis, every night, without instruments. You see its outline. The scattered stars are the surviving bright spots in a universe whose light has mostly slipped out of your visual range. The darkness is the footprint of finite time and an active geometry. Einstein did not set out to explain why nights are dark. He was trying to make sense of gravity, of inertia, of the way light behaves near massive bodies. But by making space-time itself part of the story, he laid the groundwork for a universe in which the absence of light is as informative as its presence. From here, one last step remains. To bring all of these threads together, expansion, curvature, finite age, and the faint afterglow of the beginning, and see how they finally resolve the paradox that started this journey. For now, it is enough to let one realization settle. The blackness above you is not empty. It is the visible shadow of a living space-time, still evolving, still stretching, and still, in its own indifferent way, making room for you to stand beneath it and wonder why it is dark at all. There is a moment, standing under the night, when all of this stops being theory and becomes a simple, uneasy fact. The sky is mostly dark, and somehow that darkness now feels full of history. Start with the beginning that is not really a beginning, but as far back as our equations can see, by tracing the expansion of space backward, using the measured rate at which galaxies recede. Cosmologists infer that the universe has been unfolding for about 13.8 billion years since it was in a hot, dense state we call the Big Bang. That figure is not guessed. It comes from matching models to multiple, independent measurements, the rhythm of the expansion, the composition of matter and radiation, the faint pattern of ancient light. In that early era, there was no darkness in the sense we know it. The young universe was filled with a glowing plasma of particles and light, so dense and hot that photons could not travel freely. They scattered constantly off charged particles, like beams of headlights in thick fog. Space was bright, but it was not transparent. There were no stars yet, no galaxies, only a kind of luminous chaos. As the universe expanded, it cooled. When it had stretched and chilled enough, roughly a few 100,000 years after that hot beginning, electrons and protons combined to form neutral atoms. Suddenly, light no longer bounced so often. Photons could fly almost unimpeded. The fog cleared. The universe became transparent. The glow released in that moment has never gone away. It has been traveling ever since, stretched by the expansion of space itself. What began as searing radiation in the visible and ultraviolet bands has been elongated over billions of years into microwaves. Today, that afterglow fills the sky almost uniformly, with a temperature of about 2.725 Kelvin, only a few degrees above absolute zero. If your eyes were tuned to microwaves instead of visible light, the night would not be dark. It would shine softly from every direction. A fossil light from a time long before stars formed, long before any planet cooled enough for oceans or for questions. The darkness we experience is not the absence of radiation. It is the narrowness of our senses. Even so, that ancient glow is dim. It is a background hum beneath the more dramatic, local lights of stars and galaxies. To understand why starlight itself has not filled the sky, you have to step back again and think about horizons. The observable universe is not a fixed box. It is the region from which light has had time to reach us since the cosmos became transparent, because space has been expanding while that light traveled. The edge of this observable sphere lies far beyond the simple distance you would get by multiplying the speed of light by the age of the universe. Calculations suggest that, in terms of present proper distance, the radius of our observable universe is about 46.5 billion light-years. Beyond that radius, things may exist, more galaxies, more structures, but their light has not yet arrived. Not because they are weak, but because there has not been enough time. The darkness you see when you look between the stars is, in part, the silhouette of this temporal boundary. We are looking out from inside a slowly expanding bubble of contact. The rate at which that bubble grows is tied to the expansion of space, described in broad strokes by a number called the Hubble constant. Measurements of the cosmic microwave background by the Planck spacecraft suggest a value of roughly 67.4 kilometers per second per megaparsec, meaning that every extra megaparsec of distance, about 3.3 million light-years, adds that much to a galaxy's recessional speed on average. The details are still debated, but the essential point is stable. There is a proportional relationship between distance and apparent speed, written into the fabric of expanding space. Now think again about the old paradox. In an infinite, static universe filled uniformly with stars, every line of sight should eventually hit a stellar surface. The sky should blaze with accumulated light. In the universe we actually inhabit, 3 quiet facts break that logic. First, there was a time before there were stars. The first luminous objects did not appear instantly. Observations with the James Webb Space Telescope suggest that recognizable galaxies already existed a few 100 million years after the hot beginning. One particularly distant system, JADAS GS Z13-1, appears as it was around 330 million years after the Big Bang, but that still leaves a long, starless dawn before them. No starlight can come from earlier than that, because no stars yet existed to produce it. Second, even after stars form, their light does not travel through an unchanging, rigid emptiness. As space expands, the wavelengths of photons stretch. Light that started out in the visible range from very distant sources can be shifted into infrared, microwave, or even radio frequencies by the time it reaches us. The most extreme examples of this are the photons from the early plasma, Now, the microwave background, their energy has been diluted by the growth of the universe. Third, our window is finite. We can only receive light from within that 46 billion light-year radius, and from sources that have had time to send photons since they switched on. There is no infinite stack of stellar surfaces along each line of sight. There is only a finite population of stars, in a finite observable volume, shining for finite periods. Put these three together, and the paradox dissolves. The night sky is dark, not because the universe lacks stars, but because the universe has a history. There was a time without stars. There is a horizon beyond which their light has not reached us, and there is an ongoing expansion that stretches and cools the light that does arrive. In that sense, darkness is not a failure. It is a trace of the universe's youthfulness. 13.8 billion years is a long time on human scales. But cosmically, it is still early. The observable universe has not yet had time to flood itself with visible light in every direction. We live in an era when stars are abundant, but not yet exhausted, when the microwave background is chilled, but still detectable, when galaxies are separated, but not yet fully isolated by accelerating expansion. The acceleration is its own quiet turning point. In the late 1990s, observations of distant Type Ia supernovae white dwarfs that explode at nearly uniform brightness revealed that the expansion of the universe is not slowing down under gravity alone, but speeding up, driven by something we call dark energy. The nature of this something remains uncertain. What matters here is that, as expansion accelerates, more and more galaxies will slip beyond our cosmic horizon, far in the future. Distant galaxies that are now visible will redshift out of detectability. Their light will be stretched to wavelengths so long and so faint that no conceivable telescope could register them. Our local group of galaxies, the Milky Way, Andromeda, and a few dozen smaller companions will likely merge into a single, larger system over the next several billion years, while the rest of the universe appears to thin out. To observers living then, the sky may suggest a much smaller cosmos, one in which their galaxy appears alone in a cold, dark expanse. Push the clock further, to timescales that make even the age of the universe now seem brief. If dark energy continues to behave roughly as it does today, many models predict a slow trend toward what is often called a heat death or big freeze, a state in which stars burn out. Gas is used up, and energy is spread so thinly that large-scale activity dwindles. Some estimates suggest that complex structure could fade over spans of time, at least as long as many tens or hundreds of billions of years. With more exotic processes, like the evaporation of black holes, extending the story out toward fantastical durations. Even numbers such as 10 to the 78th power years in some scenarios. There are other possibilities. Some theoretical models allow dark energy to change over time, perhaps weakening, perhaps reversing, leading one day to a halt in expansion and a slow contraction, a big crunch instead of a freeze. Recent studies have even speculated that the current acceleration might be more fragile than we think. None of these futures is confirmed. They remain arguments written in equations, constrained by data that is still being gathered. What they share is a theme: the universe, whatever its ultimate fate, does not stand still. It has a beginning that we can see the afterglow of. It has a present in which structures like galaxies and stars exist and shine. It has a future in which those structures will change, fade, or be rearranged beyond recognition. The dark night sky you see now is a temporary configuration, a particular balance between light that has had time to arrive and light that has not. Somewhere inside this changing picture, there is a human life, a narrow band of years, a local set of relationships, a handful of clear nights. You occupy a tiny epoch wedged between a blazing past and a quieter future. The photons that reach your eyes tonight may have left a star in the Andromeda Galaxy 2.5 million years ago, or a galaxy near the edge of our current reach 10 billion years ago, or the hot plasma of the early universe more than 13 billion years ago. They arrived together, layered histories on a single canvas that you simply call the sky. The paradox that started this journey asked why that canvas is mostly black. The answer, in the end, is not a trick. It is a chain of limits. Light has a finite speed. The universe has a finite age. Space has a geometry that can stretch and redshift photons. There is a horizon beyond which no signals have yet crossed. There is a future in which the signals we can see now will fade. In that light, darkness stops being an absence and becomes a map. Every patch of black between the stars is telling you something about what has not yet happened, or what has already slipped beyond reach. It is marking the difference between an impossible universe, one that is static, eternal, and infinitely filled with stars, and the universe we actually inhabit, which is none of those things. You do not have to resolve this into comfort. It can remain slightly disorienting that so much of reality is invisible, either because it lies beyond our horizon or because its light has been stretched out of our narrow band of perception. But you can recognize that, without the darkness, we would know less. The night-sky paradox forced us to confront that the universe has a story, with a before and an after. The blackness above you now is one of the clearest pages of that story. One day, long after our species is gone or transformed or forgotten, the night may look very different to whatever eyes exist then. Fewer galaxies, more emptiness, perhaps still the faint hiss of a background that has cooled even further. Whether those distant observers will reconstruct the same history we have pieced together is an open question. Many clues will have faded. Much of the evidence will lie beyond their reach. You, now, stand in a narrow window when the universe is old enough to be mapped, but young enough that its early light and many of its galaxies are still visible. You stand at a time when the night is dark enough to be puzzling, but bright enough to be instructive. In that sense, the darkness is not just something you look at. It is something you live between the echo of a beginning behind you, the hint of a quieter future ahead, and this brief, luminous middle where questions about the sky can still be asked, and tentatively answered, before the universe moves on.